Hello, everyone, and welcome to Lecture 5 of the Quantum Student Society lecture series. My name is Brady, and today we are going to be going over quantum gates and their application to qubits. Let's get started. Alrighty, so here's the agenda for today, and today we are going to be discussing the single quantum gates, the X gate, the Hadamard gate, the mathematics of the Hadamard gate, and the Z gate. Now, to understand what quantum gates are, we have to ask ourselves, what are normal gates? And these normal gates are what classical computers use to manipulate the bits. So ones or zeros, we can change a 1 to a 0 or a 0 to a 1. There's also many other manipulation techniques by these gates that we can use. However, quantum computing and quantum gates work a lot differently. For quantum gates, we don't just flip a qubit from 0 to 1, we transform the quantum state of that qubit. By changing the state, we are also changing either its probability amplitudes, its phase, or even entangling it with other qubits. You can think of them as precise rotations of a qubit state, often visualized on something like a block sphere. And this block sphere is what you see on the right. And what the block sphere does is it represents two-level quantum systems like a qubit as points on the surface of a unit sphere. It's a little complicated to understand at first, but the more you look into it, the more you'll understand. So that brings us to the question of what is the purpose of these quantum gates? These quantum gates are the fundamental building blocks of quantum algorithms. And by applying a sequence of these gates, we guide qubits through carefully designed state changes that allow quantum computers to perform computations that would be extremely hard or even impossible for classic machines. So in short, classical gates manipulate bits, while quantum gates manipulate qubit states. Now let's look at single qubit gates. These are gates that, as the name suggests, manipulate single qubits. You can think of these gates as control knobs that rotate or flip a qubit state in a very precise way. Now you may be asking, how do these gates work? And it's simple. First, a quantum algorithm is created as a step-by-step sequence of gates. Each gate is applied to a qubit, slightly changing its state, and after all the gates have been applied, the qubits are measured, which gives us a classical result we can read, like a 0 or 1. Now, if you see these images below, these are examples of single qubit states. It's not important for you to understand all of them yet. We will be discussing most of these states, most of these qubit gates in the future, and some even in later slides. So the key here is single qubit gates are the basic moves of quantum computing. And it may seem simple now, but combining these gates in the right order can build powerful quantum algorithms. Now let's talk about one of the most simple gates in quantum computing. This is the X gate. And if you're familiar with normal gates from classical computing, such as the NOT gate, this one will be quite easy to understand. Now the NOT gate, it changes the state of a bit from 1 to 0 or 0 to 1. Similarly, if we have a qubit that is in the state of 0, the X gate will flip it to 1, and vice versa. Now, what makes this different from a normal NOT gate in classical computing is the fact that we have probabilities of being either 1 or 0 in quantum computing. So, whenever you apply the X gate, it is like flipping a switch. You are turning it from 1 to 0 or 0 to 1, but you also have the probability of being 1 and probability of being 0. So you can have a 75 chance of being 1 or a 25% chance of being 0. And whenever you apply the X gate to a qubit, such as this, then you have a 25% chance of being 1 or a 75% chance of being 0. In simple terms, whatever weight or probability that was on 0 moves to 1, and whatever was on 1 moves to 0. Now on the slide, you see a matrix down here, and this matrix is showing the basics of what the X gate does. So whenever you apply the X gate to a state of 0, which from before we remember is a spin up qubit, we have this matrix right here. Whenever we solve for this matrix, we end up getting this result. And you can see between these two matrices, they're exact opposite of each other. So the 1 turns to a 0, and then the 0 turns to a 1, just like the NOT gate. Now let's talk about the Hadamard gate. The Hadamard gate is one of the most important gates in quantum computing. Its function is to create superposition, allowing the qubits to be in the 1 and 0 position all at once. Now, like the last video, we talked about classical computing, where the bit is either 0 or 1. With the Hadamard gate, we put that qubit in a state where it is both 0 and 1 at the same time, not randomly, but in a very controlled way. So if we start with a qubit that is in the 0 state, and then we apply the Hadamard gate to it, the qubit ends up being evenly balanced between both 0 and 1. Unlike the image below shows, when we measure the state of that qubit, 50% of the time it is 0 and 50% of the time it is 1. One interesting property of the Hadamard gate is that it is reversible. So if you apply the Hadamard gate to a single qubit and then apply it again, it goes back to its original state. But keep in mind, it only goes back if you have not measured the state of the qubit. Once you measure the state of the qubit, that's what breaks the reversibility. Now here's an example of the Hadamard gate in matrix form. Let's apply the Hadamard gate to a 0 qubit. So here we have the Hadamard gate applied to the 0 qubit. Now if we write this out and solve the matrix, we get that a result is 1, 1. Writing this out even further gets us this right below. So what this is saying is that the qubit is now either 1 or it is 0. So 50% chance for it being 1 or 50% chance of it being 0. And the same thing can be applied to the 1 gate. So if we have, so when we apply the Hadamard gate to the 1 state, we get this. And what it is pretty much the same as we see before, except there is a sign change right here. Now, the last gate that we'll learn about today is the Z gate. Now, the Z gate, most people would think it's kind of like the X gate. And in a way, it is similar, except the only thing that it does is it flips the 1 state while keeping the 0 state the same. And so what this is saying is that it flips the sign of the 1 state, which is also considered the phase. And this is called a phase change. Now, what it does is it does not affect the measurement probabilities by itself, but it does affect how the quantum states interact later. Now, like what we saw before with the Hadamard gate, when we apply the Z gate to a state like this, we end up getting this. So while we're not changing the probability, we are changing the state of the qubit. Like we saw before, this right here, that looks like what happens when we apply the H gate to the 0 state. And then this right here looks like what happens when we apply the H gate to the 1 state. So the Z gate is like a phase flip and not a bit flip. And now another thing that we could look at with the Z gate is how closely it is related to the Hadamard gate. We can apply an identity that gives us this. So what this is saying is the Z gate is a qubit going through the Hadamard gate, then the X gate, then the Hadamard gate again. Now that we understand individual quantum gates, let's talk about how they're actually used through quantum circuits. A quantum circuit is simply a diagram that shows what happens to qubits over time. You read it from left to right, just like reading a sentence. Each horizontal line represents a qubit, while each box represents a gate. An example of a quantum circuit is when the circuit initializes a qubit at 0, applies an X gate, and then measures a result. Now, ideally, the measurement outcome will be the 1 state with 100% certainty. However, the reality is that there is noise which can disrupt the outcome. Noise is a major challenge in quantum computing. In the real world, quantum computers are physical machines that are extremely sensitive. Small disturbances like tiny temperature changes, the inability to control electromagnetic fields, or energy leaking out of the system can all introduce errors, which we call noise. Now, noise can slightly change the state of a qubit while the circuit is running. So even if the circuit is designed perfectly, the final measurement might be wrong. So for instance, instead of measuring 100% of the time, the noise might cause a few results to incorrectly show 0. This is why noise is such a big deal. And right now, reducing and correcting noise is one of the biggest obstacles to building large-scale, reliable quantum computers. So the idea is quantum circuits show us what should really happen. However, noise explains why real quantum computers don't always behave exactly like we expect. Thank you guys for watching. I hope to see you next time where we talk more about quantum gates and introduce entanglement.